Okay, in chapter 14, section 6, we'll talk about the gradient vector. So let's take a look. So problem 1 says, find the directional derivative of f at the given point in the direction indicated by the angle theta. So the directional derivative is going to be denoted with a capital D, and then they'll use u, and then as a subscript, and then it'll be of the function, and then whatever variables we have in the function, in this case x and y. And that's going to be equal to the partial derivative of f with respect to x, which we've been working on, as a function of xy times a, and I'll get to what that is in a second, plus the partial derivative of f with respect to y, where x and y are the variables, times b, where b comes from a vector that's equal to the direction cosine theta and sine theta. So that angle they gave us will be, and this is A and this is B. So that direction they gave us will directly give us those values. Cosine theta is A, sine theta is B. Okay, so all we have to do is find partial fx and f partial y. So our function, let me write that a little larger, in this one is 2 times y times the exponential function raised to the minus x. So fx is going to equal, so if we're doing the partial of f with respect to x, everything other than x is a constant, so 2y will stick around. The derivative of e to the minus x is, you just have to bring this minus 1 down. So it's minus 1 times that stuff, which will, all we have to do is pull the minus 1 in front. Minus 1 times 2 is minus 2. Y e to the minus x. Okay, now we're going to evaluate that at the point x equals 0, 4. So let's find that now. So fx 0, 4 would be replace y with 4, replace x with 0. Oh, there's a minus in front of this. And so e to the minus 0 is just 1, and minus 2 times 4 is going to be minus 8. Okay, now we find derivative of f with respect to y, partial derivative, at xy. So our original function, y is now the constant, so the derivative of 2y is just 2, and then e to the minus x is considered a constant. Now we plug in 0, 4, and we get just 2e to the minus 0, which is 2 times 1, which is 2. So we just solved this and this. So if we can get a and b, we can multiply 8 and 2 and get the answer. So what is this vector? It would be, the theta value is 2 pi over 3, so this is going to be cosine of 2 pi over 3 and sine of 2 pi over 3. And if you go to unit circle and you look at 2 pi over 3, you will discover that the cosine of that angle is negative 1/2 in the second quadrant, and the sine value of 2 pi over 3 is root 3 over 2. And that's A and that's B. So we're going to get the directional derivative of f at this point of f at the point 0, 4 is equal to fx at 0, 4, which is negative 8, times a, which is negative 1/2, plus the directional partial f with respect to y at 0, 4, which we calculated to be 2, times b, which is root 3 over 2. This will simplify to positive 4. These 2's will cancel, and you will get square root of 3. So the directional derivative of f at the point 0, 4 in the direction indicated by the angle 2 pi over 3 is 4 plus root 3. Okay, these directional derivatives we're going to find today are, they're going to point along directions of surfaces. So we're going to have these three-dimensional surfaces, two-dimensional surfaces in some cases, and these derivatives are going to point in usually directions of maximum increase or maximum decrease, something like that. So that's the value of these directional derivatives. Okay, so that would be problem 1. Okay, problem 2 says consider the following equation. F of xy is y cubed over x, and we're doing at the point 1, 3 with a unit vector gives us of 1/3 times 2I plus root 5 times j. Okay, so it says find the gradient of f. The gradient denoted by an upside down del symbol, so Greek symbol del is a triangle. The gradient is an upside down triangle, and then it's going to be f of xy. So this is the symbol we use for this, for the word gradient. And the gradient is a vector, and it is just the partial derivative of f with respect to x and the partial derivative of f with respect to y. So we just did these partial derivatives in the previous problem. And so we will get, for this problem, the partial derivative of the original function with respect to x. So x would be a constant, so it's just going to be sorry, not x is not a constant. Y cubed is a constant. So it might help to write this like this. This is really y cubed is a constant raised to times x to the minus 1. Therefore, the derivative of that would be negative x. So bring the negative 1 down. It's going to become x to the minus 2, and then that y3 is there for the ride. Okay, the partial derivative of f with respect to y, now x is just a constant. So we can leave x on the bottom, and the derivative of y cubed is just 3y squared on top of this constant x. And I'd probably clean this up a bit and write this like y cubed over negative x squared and 3y squared over x. And I believe, yep, that's pretty close to what I have typed there. I put the minus sign next to the division symbol. You can go either top, bottom, or next to the division symbol. That's fine. And then 3y squared over x is the second component of the vector. Okay, now they want us to evaluate this gradient at the point 1, 3. So they say, what is the gradient when x is 1 and y is 3? Well, we just have to plug those numbers into this formula we have. So y is 3, so it's 3 cubed. Ugly 3. 3 cubed over x is 1, so it's minus 1 squared, comma, 3 times y squared, but y is 3, over x, which is 1. And if you do this, you will get 27 over negative 1. And we'll get 3 times 9, which is 27 over 1. And that will just be minus 27, comma 27, which is what I have there. Okay, now they want us to find the directional derivative of f in the direction of the vector u. So the way we find that is, so directional derivative, and I should have put a cap on that u. So it's a bold u, it's a unit vector, but I can't do bold really well here, so we put a little arrow on top, of f. I'm going to write this generically, and then we'll substitute the numbers we have. That equals the gradient of f at x comma y, which is a vector, dotted with the u vector. So we just have to, basically we just have to dot our two answers together. But first, yeah, I guess that's it. So we know this was minus 27, 27. And the u vector, I'm going to write it just a little bit differently. I'm going to pull this 1/3 in and write it in this arrow notation instead of the component form with i's and j's. So this is going to be 2/3, comma, root 5 over 3. So I just pulled the 1/3 into the I term and into the j term. Okay, and then if we remember the dot product, we multiply the first component with the first component, and we multiply the second component with the second component. So we're going to get the directional derivative of f in the direction of this unit vector at the point 1, 3. So we have to put x and y were 1 and 3. That's how we got these numbers up here. That would equal negative 27 times 2 over 3 plus, remember dot product, you don't have a vector anymore. We're going to get a scalar because we're multiplying and adding these components, plus 27 times root 5 over 3. But you can divide 27 by 3, it becomes 9. So this is going to be minus 18, and this is going to be 9 root 5. And that's what we have there. So that would be the directional derivative in the direction of a unit vector at a specific point. Problem 3, find the directional derivative of the function at the given point in the direction of the vector v. So this one's going to be no different. We have the directional derivative of u of directional derivative in the direction of the unit vector u of the function g at the point 1, 1 has to be the gradient of g at 1, 1 times dotted with the unit vector u. Okay, so first thing is, let's write this g vector a little larger. So it's pq. They're using, you don't have to use x and y, so they're using p and q, that's fine. So it's a vector with p's and q's in it, p to the 4th, not a vector, an equation, p squared q3. Okay, and we're doing this at 1, 1. So the gradient of g is going to equal the vector. I'm going to write this a little differently. This is g with the partial derivatives with respect to p, the first letter, and then it's g partial derivatives of q as the second letter. So this is going to equal, we look at g and the first letter that is a variable is p, and then q is a constant. So this derivative would be 4p3 minus 2pq3. So notice the q doesn't change at all, and the p's are power rule. We just bring the power down and subtract 1. So that's the first partial derivative. Now, in the second, for the second component, we look at the g equation, and now q is the variable. So p4 is going to completely go to 0 because it's like a constant. And then we're going to bring the 3 down from q3, and we have p2 and the minus sign, and then q, but no longer 3, now it's a 2. Okay, so that is the gradient of the g equation. Okay, now let's find this right away too. So the gradient of g at the point 1, 1 would be, p's and q's are all 1. So they gave us a nice number here. With 1s, all p's and q's are just going to go away basically. So it's just going to be 4 minus 2 and negative 3, which is just 2, negative 3. And we're going to dot that with the u vector, but the u vector they didn't give to us. We have to find it. It's going to be the v vector they gave divided by the magnitude of the v vector. The v vector they gave was 1, 4. Its magnitude would then be the square root of the sum of the squares of these components. 1 squared plus 4 squared. So that's going to give us the square root of 17. So the unit vector is 1 over square root 17, 4 over square root 17. And then we're going to dot that with the gradient g vector. So we have 2 minus 3 dotted with 1 over root 17 comma 4 over root 17. And just like before, we're going to multiply the first component with the first component, multiply the second component with the second component, and add those two multiplications. So we're going to get the directional derivative of g in the direction of the unit vector at the point 1, 1 is 2 over root 17 minus 12 over root 17, and we can combine those numerators into negative 10 over root 17, which is what I have there. Okay, so notice that this is a scalar, so the directional derivative of an equation at a point with a unit vector is going to end up to be a scalar value. So it's kind of like a magnitude of this directional derivative. And we'll learn later on that that can relate to maximums. So it's kind of a nice quantifiable value. Okay, problem 4, exactly the same, except now we're in 3 dimensions. So the directional derivative, the gradient, is going to have 3 components of its vector instead of 2. So this one says our function x, y, z is going to equal x e to the y plus y e to the z plus z e to the x. And we want it at the point 0, 0, 0, and our vector is 6, 2, minus 1. So first we find the gradient of f, and we look at, now in three dimensions, the well, let me write. This is fx, this is fy, this is fz. So if we look at this equation, x e y is the only term that's going to stick around. So this x e y, so x e y is going to be a constant, and x is going to become 1, so this is going to be e to the y. Then the other term that has an x in it is zex. Well, z is now a constant, and e to the x, the derivative, that's just e to the x, so this would be plus zex. Now y is going to be very similar, so I have 2 terms with y in it. The first is x e y. The derivative of ey is ey, and x is a constant, so that's going to be x e y. And then the second term is y e z. Well, y, ez is a constant, and the derivative of y is 1, so that's going to be ez. Comma, last term z, we have yez is going to be yez, and zex is just going to be ex. So if I look, there should be symmetry here. I should have an e and an exponent, and then a letter e and an exponent in each term, and we do. But that's a lot of writing, so we want to get rid of that as soon as possible. So we're going to plug in our numbers right away. They want this at 0, 0, 0. That's going to be e to the 0 plus 0 e to the 0, 0 e to the 0 plus e to the z, but z is 0, comma, y, which is 0, e to the z, which is 0, plus e to the 0. And they gave us really nice numbers because a lot of stuff's going to go away. E to the 0 is 1. So this is going to equal 1 plus 0. Let me not write the plus 0. So it's just going to be 1, because 0 times anything is 0. So these 0 E0 terms are going to go away, and all E0 terms are 1, so you're going to get 1, 1, 1. Okay, now the only other thing we have to do is dot that with the u vector. Well, the u vector is going to be the v vector. I better write that part. It's going to be the v vector divided by the magnitude of the v vector. And the v vector is 6, 2, minus 1. And the magnitude of this would be 6 squared plus 2 squared plus minus 1 squared, square rooted, and we're going to get from that, that's the square root of 41. So we're going to have 6 over root 41, 2 over root 41, and minus 1 over root 41. But we're dotting that with just a bunch of ones. So it's going to be 6 times this one, 2 times this one, and minus 1 times this one. So in essence, when we dot those two vectors, it's just going to be exactly the u vector spit back at us, but everything's going to be added together. So the directional derivative of f in the direction of u, it's hard to say this, at the point 0, 0, 0, is just 6 over root 41 plus, so the dot product is going to turn these multiplications into pluses, 2 over root 41 minus, because it's plus negative 1 over root 41, which is just 8 minus 1, which is 7 over root 41. So all that work for a scalar value, just some number, you can plug it in your calculator and figure it out, just some decimal number. Okay, that's problem 4. Okay, problem 5 is going to be a very similar problem. We have to find a directional derivative again, and we're given the function x and y is the square root of xy, which I'm going to immediately change to xy raised to the 1/2 power. You'll see why I do this in a second. And this one's at the point 2, 8, and then it's going to point Q, which is 5, 4. So we have 2 points in space, and we want to find the directional derivative from P to Q. And it just adds one very simple step of calculating the v vector ourselves, and then it's exactly like the previous two problems. From P to Q, so this is basically the directed line segment from P to Q, it would just be the Q component minus the P component, and then the Q second component 4 minus the P first component 8, and we're going to get the v vector is 3 comma minus 4. And now it's really similar to the last couple problems. Okay, so first we're going to find the gradient of f at the point 2, 8. So you do use the first point P for your numbers that you're going to plug in for x and y. And it's going to be, actually let me do the x and y first, and then I'll plug in the 2, 8. So let's do it generically xy. So the derivative of this with respect to x would be bring the 1/2 down, leave the parentheses by itself, subtract 1 from 1/2, and it gives you minus 1/2 times the derivative of the inside. Now the derivative of xy, if x is the variable and y is the constant, would be y times the derivative of x, which is 1, so it would be times y. And then it's going to be exactly the same when we take this derivative with respect to y, 1/2 xy to the minus 1/2. But now y is the variable, x is the constant, so the derivative of xy when y is the variable becomes just the constant value x. And we can just leave it like that. Maybe not. Let me write it. Maybe it's a little clearer to write it like this. So this would be y over 2 square root xy. And this would be x over 2 square root xy. Okay, but now we're going to plug in our number. So this is at the point 2, 8. So this would be equal to y is 8 over 2 times the square root of 2 times 8. And this is x is 2 over 2 square root of 2 times 8. This is going to be, I'm not going to have enough room there. This is going to be 8 divided by 2 is 4 over the square root of 16. 2 divided by 2 is 1 divided by the square root of 16. Nice round number. This is 4 over 4. this is 1 over 4. So the gradient is 1 comma 1/4. Okay, that's the gradient. Now we're dotting it with the u vector. Well, we haven't found the u vector yet. The u vector is v over magnitude v. V vector we found to be 3 comma negative 4. Therefore its magnitude would be 3 squared plus minus 4 squared, which is 9 plus 16, which is root 25, which is 5. So this is going to be 3/5 comma minus 4/5. And again, we're going to dot that with this other vector we found. So we're going to multiply the first two components, multiply the second two components, and add them. So we're going to get the directional derivative of f at point 2 comma 8 in the direction of the unit vector u is equal to 3/5 times 1, so that's just 3/5, plus negative 4 times 1/4, which will just be negative 1/5. And we can combine that. 3 minus 1 is 2 over 5. And that would be the directional derivative of f at 0.28 in the direction of q, in the direction of PQ. Okay, problem 6. Let's see. Are we changing it up at all? Yes, we are. So we're going to do something a little different now. It says find the maximum rate of change of f at the given point and direction in which it occurs. So the maximum rate of change for problems like this is equal to the magnitude of the gradient vector at whatever point we're evaluating. So it's pretty simple. We just have to find the gradient like we've been doing and then find its magnitude. So let's see what kind of equation they gave us. xy is 4y root x, which I'm going to immediately change to 4y x to the 1/2. Therefore, the fx component would be 1/2, let me write it all out, 4 times 1/2, y is a constant, x to the minus 1/2. So the 4 and the 1/2 are going to become 2, and we're going to get 2y on top and the square root of x on the bottom. So that would be the partial derivative of f with respect to x. Fy is going to be, now y is the constant, this one's a little easier, so it's just going to be 4y goes away, x to the 1/2. Okay, now we're evaluating this at 0.43. So the gradient vector of f at the point 43 would be equal to 2 times 3 over the square root of 4, just replacing y and x with 3 and 4, and then it would be 4 times the square root of 4. This is going to be, square root of 4 is 2, so these two, the 2 and the square root of 4 will cancel, and we're left with 3, and then 4 times square root of 4 would be 4 times 2, which is 8. So 3 comma 8. Now we just have to find the magnitude of that. Well, that's going to just equal the square root of these components squared. So 3 squared plus 8 squared, which is 9 plus 64, which is 73. That is the answer to the maximum rate of change. Okay, now the direction vector is just taking the direction vector is just taking the gradient of f and dividing by its magnitude. So this direction vector, I should have written that, is the gradient of f divided by its magnitude. Well, the gradient is 3, 8, and its magnitude is root 73. So you just get a vector now, 3 over root 73, comma 8 over root 73. So almost nothing to do there. We had all those numbers already, and so we get the direction vector. 6. Problem 7. Find all points at which the direction of fastest change of the function fxy equals x squared plus y squared minus 4x. Let me write this. So here's our function. So we can actually see it. X squared plus y squared minus 4x minus 8y. And it says we want the direction vector to be ij. So in direction one I plus 1j. Okay, so for this one, we just have to find the gradient vector and put it equal to this one, this direction vector. So basically, this is the direction vector 1, 1, and we're just going to set that equal to the gradient vector and solve. So the gradient vector on this one, let me not be sloppy with the nomenclature here. This would be xy. So the derivative of this function with respect to x would be 2x, y squared goes away, minus 4x becomes minus 4, and negative 8y goes away. That's the x term. The partial derivative of f with respect to y would be 2y, the x squared goes away, the 4x goes away, minus 8. And now we're setting this equal to 1, 1. So we're going to get 2x minus 4. So from this we get 2x minus 4 equals 2y minus 8. So since these components are the same, this is 1 and this is 1, we can in essence just equate these two. So basically this says, okay, if this x and y are the same on this side, then these two terms, and I gotta be careful not x and y, if this I term is equal to this j term on the right, then this I term has to equal this j term on the left. So we can equate these two. Okay, now we can solve this, and generally we want to solve this for y. So we're going to add 8 to both sides and get 2x plus 4 equals 2y. So I got rid of this minus 8 by adding it to minus 4. Adding positive 8 to minus 4. Now divide everything by 2. And therefore the equation that takes the rate of fastest change of this function and points it in the direction ij is x plus 2 equals y, which is what I have there. Okay, so not too bad. Just a gradient and then setting it equal to the direction vector that they gave us. Problem 8. Find the equation of the tangent plane and the normal line to the given surface at the specified point. So we know that the gradient of a function at xy and some point xyz or xy in 2 dimensions versus 3, that's going to be perpendicular to a level surface where that level surface is defined by f of xyz equals some constant c. So I'll put some constant, but I'll typically just call it c. Okay, so in this one, it's almost equal, this function is almost equal to a constant, but they have 3e xyz, which is actually a variable. So what we're going to do is we're going to call f of xyz, we're going to let that equal x plus y plus z minus 3e to the xyz. And when I subtract that, 3e xyz over the right hand side is 0. So this function is equal to a constant. That constant is 0. And so our function is really going to be x plus y plus z minus the 3e xyz. And now we just have to find the gradient of that. So the gradient of this function at the point xyz has to be equal to, well, the derivative of x is 1, y goes away, z goes away. Now this one would be minus 3 yz e to the xyz. Now how did I get that? So if I look at minus 3 exyz, x is the variable, so yz is a constant, and the derivative of e raised to a constant times a variable is the constant comes down. So y and z will come down in front, and then everything stays the same. Now using that same pattern, we're going to get 1 for y, x and z will go away, and we're going to get minus 3. This time y is the variable, so xz will come down, and then it'll be e to the xyz. Last term, z is 1, minus 3 times xy are now the constants, e to the xyz. Now luckily they gave us a nice point again. The point is 0, 0, 3. So all x's and y's are 0, and z is 3. I guess I'll write it, but really I don't have to write this because anything that has an x or y in it's going to totally get wiped out. So this 0 right here is going to kill everything in this. So this whole thing is just going to be 1. And by that same argument, everything's going to get killed off in this gradient except for the 1s and the 1s. So we get a very simple and nice gradient vector. It should just be 1, 1, 1. So our gradient vector at the point 0, 0, 3 is 1, 1, 1. And we're going to call that A, B, and C. So we had seen this back when we had talked about perpendicular planes, where we find a vector and we call the vector the components A, B, and C, and then they become coefficients on the equation of a plane. So in fact, what we're going to get for this is a plane is described by A times x minus x0 plus B y minus y0 plus C z minus z0. And that's going to equal 0. Well, our point, the point they gave us was, let me write it right here. The point they gave us was 0, 0, 3. Well, that's also x0, y0, and z0. So we know everything for this plane equation. A, B, and C are all 1. x0 is 0, y0 is 0, z0 is 3. So I can write this. A is 1, x is x, x0 is 0, B is 1, y is y, y0 is 0, C is 1, z is z, z0 is 3. So be careful, you have a number there equals 0. And if you expand this out, you get x out of this, y out of all that, and you get z minus 3 here equals 0. So we're just going to move the 3 over. We have x plus y plus z equals positive 3. And that's what we have right there. So that's the tangent plane. Okay, now we want to find the normal line, and we're going to use parametric form. So we're going to have x as a function of t, y as a function of t, and z as a function of t. Well, the form for that, if you recall when we did parametric lines, was x is equal to x0 plus at, y was equal to y0, and I should say, again, don't let me be sloppy with the way we write this. This is x of t. This is y of t. Z of, oops, I didn't finish that one. This is going to, y of t is y0 plus bt, and z of t is z0 plus ct. Well, again, we know x0 is 0, we know a is 1, and t is t. For y of t, we know y0 is 0, b is 1, and t is t. For z0, that's 0, but c, not 0, z0 is 1. Boy, where am I tonight? z0 is 3. c is 1 times t. So we're going to get x of t is just 1t, which we'll just write as t. And y of t is 0 plus 1t, which we'll just write as t. And then z of t is 3 plus t. Just dropping those leading 1 coefficients. And we wrote those here. So they want you to write those in point form, but use commas. So it's t, t, and 3 plus t. Okay, that's problem 8. Okay, problem 9, they say the equation of the tangent plane to the ellipsoid x squared over a plus y squared over b squared plus z squared over c squared equals 1 at the point x0, y0, z0 can be written as x0 over a squared plus y0 over b squared plus z0 over c squared equals 1. And then they want us to change it from an ellipsoid to a hyperboloid and prove a similar equation. So I'm going to show you this. I'm going to show you how they got the first one, and then we're going to use a shortcut to get to the answer. Okay, so we just have to take the gradient. So what we have is, let me write it bigger. F of x, y, z is equal to x squared over a squared plus y squared over b squared plus z squared over c squared equal 1. Well, the gradient of this is equal to, when I take the partial derivative of f with respect to x, y squared, z squared, 1, they all go away. So all I'm left with is x squared. The derivative of that is 2x on top of a squared. Then similarly for y, everything's going to go away except for y squared over b squared. Derivative of y squared is 2y over the constant b squared. And then derivative of z squared is 2z over the constant c squared. So that is the gradient of that function. Okay, now they want us to put the gradient in at the point, so they want us to find the gradient at the point x0, y0, z0. So we're going to have let's see here. Do I have room? I don't. So the gradient of f, when I change x to x0, y to y0, and z to z0, is pretty much the same thing. Just add a subscript 0 on each term. 2x0 over a squared, 2y0 over b squared, 2z0 over c squared. And if you recall, those are going to be, and I definitely need color here, those are going to be a, b, and c, the letters in front of the plane equation. So the plane equation, let's write it again, was a, x minus x0, plus b, y minus y0, plus c, z minus z0. All that equals 0. But a, b, and c are going to come from these three terms up here. So this is going to be 2x0 over a squared times x minus x0 plus 2y0 for b over b squared, y minus y0, plus 2z0 over c squared times z minus z0. So all I did was replace a, b, and c with those three terms from our gradient vector. Okay, now we're going to have to distribute this term into this one and into this one. And then 2y0 into this one and 2y0 into this one. 2z0 into this one, and 2z0 into this one. Now I need a lot of space for this. We're going to get 2x0 times x over a squared minus 2x0 squared over a squared plus 2y0 y over b squared minus 2y0 squared over b squared. So those four terms account for the first four purple arrows I drew, just distributing everything. Then we're going to get plus 2z0 times z over c squared minus 2z0 squared over c squared, and all that equals 0. Okay, now, boy, this is a heck of a problem. We're going to group things, so anything with an x, y, or a z, we're going to keep on the left. Anything with a x0 squared, y0 squared, z0 squared, we're going to move to the right. So we're going to get a room. We're going to get let me do this right up here in this little space. Two x0x over a squared plus 2 y0y over b squared plus 2 z0z over c squared. That's going to equal. Now all these negative 2's right here are going to become positive, and I have to do one step just to save a space. I'm going to pull out the 2, and we're left with x0 squared over a squared plus y0 squared over b squared plus z0 squared over c squared. But that whole thing has to be equal to 1. So if you have x squared over a squared, y squared over b squared, z squared over z squared, and you put in a point that satisfies that function, like x0, y0, z squared, z0, that should also be equal to 1. So if we're plugging in, if this has the exact same form as this up here, and then we said that's equal to 1, this whole bubble is equal to 1. So what we get is this whole thing on the left is equal to 2 times 1, but there's a 2 in front of all those things, so we can basically cancel all the 2's. I hate that I have to do all this without showing it because I'm running out of space. But basically, this 2 is going to cancel with these 2's are all going to be divided out, and this 2 is going to become a 1. And this whole thing became a 1. So the right-hand side is just 1 times 1, and the left side is x0x over a squared plus y0y over b squared plus z0z over c squared, and the right is just 1 times 1, which is 1. So in effect, we just proved right here, we just proved this equation. So x0x over a squared plus y0y over b squared plus z0z times z0 over c squared equals 1. Now notice I did transform the z and the z0 and x. It doesn't matter though. So I can write the x0 first or the x0 second. It doesn't matter in multiplication. So we just proved that. Now here's the shortcut. I'm going to clear all that away. In the hyperboloid, the only difference in the hyperboloid is instead of a plus z squared over c, there's a minus z squared over c. And it turns out that if you, so this plus changes to a minus. If you go through that whole process again, but there's a minus sign there. All it does is change this plus to a minus. So all you have to do is retype this equation and change the second operator from a plus to a minus. And that's all that minus is going to do. So the hyperboloid, the equation of the tangent plane is almost exactly the same. We just have a minus sign that shows up. Okay, last problem, problem 10. Determine whether the statement is true or false. The directional derivative in the k direction of the function xyz has to equal just the partial derivative of f with respect to z at x, y, z. Okay, well, the gradient of f x, y, z would equal the vector fx, fy, fz. And I should be writing a parentheses x, y, z next to each of those, but let's, just for the sake of argument, not write all that. And then the k vector is the unit vector 0, 0, 1. So the directional derivative of k of the function x, y, z would equal the gradient vector fx, fy, fz dotted with the k unit vector. This is a unit vector dotted with the unit vector 0, 0, 1. Well, based on dot products, it's going to be fx times 0 plus fy times 0 plus fz times 1. So everything is going to go away. Fx goes away, fy goes away because they're multiplied times 0. And this is going to equal 1 times fz, which is the partial derivative of f at the point x, y, z. I was just not writing the parentheses part, but it was there all along. And that's exactly what they said, so that's a true statement. Okay, and now we'll conclude Chapter 14, Section 6.